So for our next problem, we have the problem of building a rectangular picture frame. So, and as you can see, a lot of these problems involve things like rectangles. Anyway, a picture frame has to enclose a 1600 square inch portrait, a fairly large portrait. The frame is going to be made in such a way that the left, right, and bottom of the frame are made of a material that costs $40 per inch, and the top is made of a material that costs $120 an inch. So you might imagine that perhaps the framing material on the left, right, and bottom will be mahogany, and the top will be made of silver or something like that. So here's the thing: if you want to start with with figuring out what the quantity to be optimized is. It's certainly easy to make the mistake that because this involves a rectangle, we must be trying to optimize the area. But note that we're given the area. There's nothing to optimize because there's no choice but to make a 1600 square inch picture. The uh, the thing to be optimized is we want to find the smallest cost that we can build this frame for, keeping in mind that the top is going to cost 120 per inch, and the and sides and the bottom are going to cost 40 per inch. So it's the cost that we want to optimize, not the area. And in a little bit of a twist, what turns out to be the best cost is not going to be the maximum cost, but the minimum cost. And we can use the same sort of procedure to find either one. So what we need to do is write an objective function. So what we have here is we're going to have a rectangle whose dimensions are x by y. So let's say the vertical part of this rectangle has a length of y, and the horizontal part has a length of x. So we could certainly write that the area is equal to xy, but the problem is, go back a couple of videos. We're in single variable calculus. We have to be able to write everything as a function of one variable because we don't have the tools to optimize a function in two variables yet, which means that I'm going to have to get rid of one of these variables, either x or y. Since most people like to work in x, I'm going to get rid of y. So the thing to observe here is that whatever xy is, it has to be equal to 1600, and therefore y must equal 1600 over x. So therefore, what I have is what I have here is an expression for y in terms of x. It means that I can write the cost. Let's figure out what the cost function is going to look like. The cost is going to equal, this is a side of length y, that's x, and that's going to be x. So the cost is going to be equal to 40 times x plus 40 times y plus 40 times y plus 120 times x. So because the two y sides are both going to cost $40 each, one of the x sides costs $40 per inch, one of the x sides costs $40 per inch, and the other x side costs $120 per inch. So since x and y are all numbers of inches, these are giving the cost of making each of the sides, and we're just adding them up. So that's going to equal, let's see, that's going to equal 160x plus 80y. And since we've written y in terms of x, that's going to be 160x plus 80 times 1600 over x. Okay, so let's write the function c of x is equal to 160x plus, this is going to be 128,000. That's 80 times 1600 over x. So this may turn out to be a little bit more convenient if I write it in the form 160x plus 128,000x to the minus 1. So there is our objective function. C of x equals 160x plus 128,000x to the minus 1. All right, now, what's the feasible domain here? Well, certainly the smallest that I can make x is 0. In fact, I can't really make x 0 because that would be divisible by 0. That would involve division by 0. So the domain is going to be 0. I'm going to exclude the endpoint 0. And what's the largest I could make x? The answer is there is nothing largest. I mean, is it a million? Sure, I can make with the width of a million, sure, I can make a 1600 square inch picture frame. It's going to be very, very long and short, but it's possible. Is a billion the most that I can make x? A trillion? There's no limit. I can make anything. So this is going to be all positive numbers. So the domain is 0 to infinity. This is the first time that we've encountered a problem where the domain is not a closed and bounded interval, so we're going to have to be a little bit clever about how we verify that we've actually found the least cost as opposed to, let's say, the most cost, and I'll show you how to do that. So, okay, so what we're now going to do is we're going to optimize. We're going to optimize, let me put it up here so we can see the picture. Let's go here. We're going to optimize c of x on the interval 0, infinity. So let's find the critical points. C prime of x is going to equal 160 minus 128,000 x to the negative 2. All right, so what we want to do is solve. This, by the way, is equal to 160 minus 128,000 over x squared. So what I want to do is solve for when this expression is 0. We can see that it is undefined at 0, but we've already determined that x equals 0 is not in the domain any place. There's no place in the domain of C that the derivative is undefined. So we're just looking for places where it's 0. So what I'm looking for is where 128,000 over x squared is equal to 160. That's going to give me 0. So that means that 128,000 is equal to 160x squared. That gives us x squared is equal to 128,000 over 160. Let's come up here. That gives us x squared equals 800. That gives us x is equal to plus or minus the square root of 800. We can actually simplify that a bit. We don't need the negative value because we already know the domain is just the positive numbers, so I'm just going to disregard that negative sign. The square root of 800 is equal to the square root of 8 times the square root of 100. That's going to be, square root of 100 is 10, and square root of 8 is 2 root 2, so that's going to be 20 root 2. This is the critical point. It's very likely that that's going to give us the answer, but we want to validate that it actually gives us the answer. Remember, we're looking for the least cost, and the critical point might turn out to be a min, a max, or neither. So we're going to have to use one of the possible ways of determining whether a critical point is a local min or a local max, or neither. So recall that the two ways to do that are either the first derivative test, where we check whether the function changes from positive derivative to negative derivative across the critical point, or vice versa, or we use the second derivative test where we look at the second derivative of the function at that point to determine whether this critical point is sitting on top of a concave down function or below a concave up function. The second derivative test is actually going to be pretty straightforward in this case. So let's use that. Let's find c prime prime of x. Look up here at the expression for c prime. We're going to differentiate that. This 160 is just going to, the derivative of that is 0. So the derivative of negative 128,000 x to the negative 2 is going to be negative 2 times negative 1. So it's going to be 2 times 128,000. That comes out to 256,000 x to the negative 3. And we can easily see that for any positive number x, if I multiply it by positive 256,000, I'm going to get a positive number. So this is always going to be greater than 0 on the domain 0 to infinity. That means that the function is always going to be concave up, and it means that any critical point is sitting at the bottom of a concave up function. So we have in fact verified that this is in fact the minimum value. That x equals 20 root 2 does give the minimum value. So finally, let's finish the problem. We know that y is equal to 1600 over x, so that's going to be 1600 over 20 root 2. That gives us 80 over root 2. So the dimensions of the picture frame are, this is the answer, the dimensions of the picture frame are going to be 20 root 2 by 80 over root 2. And this is, of course, going to be inches on either side. So that's the answer. Those are the dimensions of the picture frame, where this, by the way, is the x and this is the y. So that's the vertical, and the x is the horizontal, y is the vertical. So the dimensions of the picture frame that we want to make are 20 root 2 inches by 80 over root 2 inches, and that will be the picture frame that we can construct for the least cost.